Right, well, here we are. We're going to continue our conversation about Lewis structures and formal charge by attempting to answer the question which compounds have nonpolar covalent bonds, which have polar covalent bonds, and which have ions. Now, we're going to use parts A and B to illustrate the point, and then parts C and D as just kind of exercises, because there are three basic types of bonds that we have to illustrate. And I will go ahead and tell you that lithium fluoride forms ions. What that means essentially is that lithium, when it bonds to fluorine, what actually happens is fluorine sucks all of the electrons to itself and leaves you with a positively charged lithium ion and a negatively charged fluoride ion. When it's in its solid form, these ions kind of pack together and form crystals, and then when it's dissolved in something, the ions just go and float around in solution. But the way that we know this is by looking at their electronegativity, because it is electronegativity in the end that determines how different bonds are made. So we'll say, for the time being, that ions are formed in the lithium fluoride, but we'll look to see why that happens. Lithium is over here in group 1, and fluorine is over here in group 7. So fluorine needs one electron to get a full octet and is very electronegative. It is the most electronegative element of all. And lithium is among the least electronegative. I mean, I guess you can go down here and get, say, cesium or francium. That's less, but lithium is pretty readily losing its electrons in a bond, especially given the fact that it's just one away from becoming a noble gas. It's one electron more than helium. But especially given how small fluorine is and how positively charged its nucleus is, it'll just suck all the electrons away. Now, the way we can go and quantify this is by looking at the electronegativity, which is 3.98 of fluorine, whereas it's only 0.98 in the case of lithium. So the difference in electronegativity tells us about the nature of the bond. If the difference in electronegativity is bigger than 1.9, if it's bigger than 1.9, ions will form. It will be an ionic bond. So 3.98 minus 0.98 gives us a difference of 3, which is definitely more than 1.9. In the case of floral methane, we are dealing with a little bit more interesting situation because we have a carbon bonded to 3 hydrogens. Hydrogen 1, hydrogen 2, and hydrogen 3, and for all intents and purposes, all those bonds are basically the same. But it's also bonded to a fluorine. So we're going to have to look at the carbon-fluorine bond, this one here, as well as at the 3 carbon-hydrogen bonds there, there, and there. So that means we need to look at the electronegativity difference between hydrogen and carbon and fluorine. So the electronegativity of hydrogen is 2.20. You can see up here in the top left, 2.20. The electronegativity of carbon is 2.55. And the electronegativity of fluorine, as we talked about before, is 3.98. So we have 2.20, 2.20, 2.55, and 3.98. So the electronegativity difference in the carbon-hydrogen bond is 0.35. That means that our carbon-hydrogen bond is nonpolar. Nonpolar covalent.
And our carbon-fluorine bond, 2.5, 3.5, so that will give us 1.43, which is in the quite polar range of the polar covalent category. So the carbon-fluorine bond is polar covalent. Now, what does this mean? This means essentially that when we have a carbon bonded to a fluorine, let's say we'll just look only at this carbon-fluorine thing for a moment. Just forget about the hydrogens for the time being. When we have carbon bonded to fluorine, fluorine will assume a partial positive charge or a partial negative charge, and carbon will assume a partial positive charge because fluorine is sucking more of the bonding electrons toward it with an electronegativity of 3.98 than is carbon with an electronegativity of only 2.55. But then when we look at the carbon-hydrogen bond, the electronegativity difference isn't all that much. Yes, I guess you could go and say that carbon is going to be sucking more of the electrons than hydrogen, but it's not enough for us to actually consider it to be polar, and so we don't. So now the next two are going to go relatively quickly because we're just going to solve the problem and be done. So we look at the electronegativity of magnesium. We're going to need the electronegativity of magnesium. We're going to need the electronegativity of chlorine. We're also going to need the electronegativity of hydrogen, which we found was 2.20. Magnesium, I think, is 1.31. Yes, we find this here in group 2. And chlorine is 3.16. Chlorine has an electronegativity of 3.16. And magnesium has an electronegativity of 1.31. So for the magnesium-chlorine bond, we have a difference of 1. What is that? 1.75. 16. I can't even do my math here. 3.16 minus 1.31. So we'll just do it the right way. 6 minus 1, 5. 10 minus 3 is 7. 2 minus 1 is 1. Oh, well, I was right. It is 1.75. And then the difference between chlorine and hydrogen is 0.94. 0.94. Both of these are polar covalent because the difference in electronegativity is in between 0.5 and 1.9. So both of these are polar covalent. And while putting this problem together, I was also thinking about a bonus problem. And that would be calcium chloride. Because calcium is also in group 2, but it's further down. Calcium is further down in the group than is magnesium. It's just one further down, but it has an awful lot more. It's percentage-wise a lot bigger than magnesium chloride. So calcium has an electronegativity of 1. It's very close to lithium. And chlorine has one of 3.16. So calcium chloride has an electronegativity difference of 2.16, which gives us that ions are formed. Now, why do I bring this up?
Because in general chemistry, we talked about this idea of freezing point depression. That basically, if you have things, say, dissolved in water, for example, like you have one calcium with a charge of 2 and two chlorides with a minus charge, those will go, and you will have 3 particles, the calcium and 2 chlorines. That will decrease the melting point of water. So what people like to do is during the winter, some people will put calcium chloride on the streets in their cities and use it to de-ice their driveways and so on. Why does this work? It works because if you put enough magnesium chloride and it dissolves in enough water, it will prevent the water from freezing, or even if you kind of mix it in with the ice and it gets mixed in, it'll allow you to have a layer of water rather than a layer of ice on top of things. This would only happen, though, because calcium chloride forms ions. Calcium chloride forms ions, whereas magnesium chloride, same general look, 1 magnesium, 2 chlorines, is only a polar covalent bond. So they're more strongly attached to each other rather than just splitting up into their constituent parts. Magnesium is kind of a special element in that regard because it's still small enough to do a whole lot of things, and very light. So, thank you for tolerating my little tangent here. And we'll take a look at what we're going to do next time. Next time we're going to just work on looking at the polarity of bonds and using the appropriate notation to show about polar bonds, which way the polarity is, and so on. This relates an awful lot more to later chapters where we'll be discussing the flow of electrons. So here we're just focused on how they are statically in one compound, but then over time we're going to be talking about electron flow. Look forward to seeing you next time. Goodbye.